Solve the differential equation d square y by dx square minus 5 times dy by dx plus 6 times y equals e raised to 3x. Notice that this differential equation is non-homogeneous type because we have the RHS, which is r of x is non-zero. That is, e raised to 3x, which is a function on independent variable x, is a non-zero expression, and hence in order to compute general solution we will have to compute two parts, which is complementary function CF and particular integral PI. The given differential equation can be written as capital D square minus 5 times D plus 6 applied on y equals e raised to 3x, where we treat the RHS e raised to 3x as r of x, which is a function on independent variable x. Here we have made use of the differential operator capital D equals d by dx. In order to find out complementary function, we will find out the auxiliary equation corresponding to the given differential equation, which is obtained by replacing capital D by m. Thus we have m square minus 5m plus 6 equated to 0. Always auxiliary equation will have RHS equated to 0. When you solve the auxiliary equation, we will obtain two roots, m1 equals 2 and m2 equals 3. Here auxiliary equation is a quadratic equation, and that's why we have obtained two roots. Since the two roots are distinct, we have complementary function written as c1 e raised to 2x plus c2 e raised to 3x. c1 and c2 are arbitrary constants. We can write it as capital A times e raised to 2x plus capital B times e raised to 3x. In place of constants c1 and c2, any other representation of constants are also possible, like a1 e raised to 2x plus a2 e raised to 3x and so on. Because the selection of constants c1 and c2 are just arbitrary. Now we will find out particular integral. Pi equals 1 by f of d acting on RHS, which is e raised to 3x. We have f of d is d square minus 5d plus 6. Whenever we have r of x is an exponential function where a is the coefficient of x in the power part of exponential function, we will give d equals a in the expression of f of d. That is, here we have f of d equals this expression, and a, which is the coefficient of x in the power part of exponential function, is 3 here. When you give d equals a in f of d, we observe that f of d becomes 0 at d equals 3. We have f of 3 equals 3 square minus 5 times 3 plus 6, which becomes 0. Since the denominator becomes 0, when we give capital D equals a, which equals 3 here, the general rule to compute Pi is that whenever the denominator becomes 0, when you give capital D equals a, the rule is that we will take the derivative of f of d with respect to d, and that is written here. That is, the denominator becomes f dash of d. Simultaneously, we have to multiply the numerator with x. Hence, whenever you have f of a equals 0, in order to compute particular integral, we have Pi equals x multiplied to 1 by f dash of d, which acts on RHS e raised to ax. Here we have f of d equals d square minus 5d plus 6. When this expression is differentiated with respect to capital D, we obtain f dash of d equals 2 times d minus 5. In this expression f dash of d, when you give capital D equals a equals 3 here, you notice that f dash of d at capital D equals 3 is not becoming 0. That is, in the expression 2d minus 5, which is f dash of d, when you give capital D equals 3, you obtain 2 times 3 minus 5, which is a non-zero value. Hence we have Pi will be x times 1 by 2 into 3 minus 5 multiplied to e raised to 3x. Therefore, corresponding to the RHS r of x equals e raised to 3x, we obtain Pi equals x e raised to 3x. Hence we have general solution equals Cf plus Pi, which equals c1 e raised to 2x plus c2 e raised to 3x plus x e raised to 3x.